Hey, welcome to section 5.5, where now we're going to be talking about rational functions. Um, and so simply put, a rational function is just a function that's two polynomials divided by each other. So it's p of x divided by q of x, where p of x, q of x are polynomials. This is an important time to remember that constant functions are also polynomials. So for some examples, 1 over x is a rational function with the polynomials 1 and x. But we can also have more complicated ones like x cubed minus 1 over x to the 5th plus 5x plus 2. All right, but before diving into the math that's going on, I thought we'd warm up with just a few applications of rational functions, kind of where they pop up, and why maybe we don't encounter them too often. So the first one I want to talk about is an example with miles per gallon. So let's give an example of 3 cars. You have one that makes 15 miles a gallon. Maybe that's a Ford F-150. I drive an 07 Acura. That gets about 30 miles to the gallon on the highway. And then my mom drives a Honda Civic, and at the speed she's driving, she gets 60 miles to the gallon. So typically, I like, through most of my undergrad and my master's, I would drive from Ventura, where my parents live, to San Luis Obispo, where my school is, or school was. And so that was 120 miles. All right, so if I'm driving, depending on which kind of car I'm driving, I might wonder how many gallons of gas I'm going to use, because, I'm a poor college student. I want to make sure that I'm getting a good value. Now, it seems like, well, we already know, like the Honda Civic getting 60 miles per gallon, that's going to be the one that's the most fuel efficient. But it's worth doing an analysis of how much better it is. So we can create a function, we'll call it capital G of x, where x is the fuel efficiency. And we're going to output the number of gallons that we use over 120 miles. So if we think about it, the number of gallons we have to use is going to be, first, we have to drive 120 miles. And then over here, we have this in miles per gallon. So let's translate that to gallons per mile. So we can look at our g of x as, get rid of that 120 for a second, as miles times gallons per mile. So since we measure, we're plugging in fuel efficiency, which is miles per gallon, gallons per mile just equals 1 over miles per gallon. So erasing the text, we get that our g of x is miles traveled times 1 over miles per gallon. So it'll be 1 over x, or 120 over x. So that's our function for how many gallons we have to use based on our fuel efficiency. And let's investigate the 3 values. We want to know g of 15, g of 30, and g of 60. And so we just plug those numbers into our function. We get 120 divided by 15, 120 divided by 30, 120 divided by 60. And that gives us 8, 4, and 2. So what this is saying is that if I switch from a car that gets 15 miles per gallon to 30 miles per gallon on this drive, I'm going to save 4 gallons of gas. So it's a pretty big improvement. But if I switch from a car that gets 30 miles to the gallon to driving my mom's car, I'm actually only saving 2 gallons. So it's not as significant. Even more so, if we look at a car that gets 120 miles per gallon, we get 120 divided by 120, which is 1. So yeah, we've doubled fuel efficiency, but all we've done is half how much gas we're using, which is actually kind of interesting to think about, because when you get to these higher numbers, it matters less what your fuel efficiency is because of what's going on with the division here. Like we have that adding 15 mpg going from 15 to 30 saves us 4 gallons of gas. If we go from 60 to 75, we're going to go from 2 to something bigger than 1.5. So we save less than a half gallon of gas there. So it might seem a little paradoxical, but it's just because we're dividing instead of multiplying. So we're not necessarily scaling linearly. So this is something to keep in mind if you're thinking about buying a car, and if you're looking at the difference between 58 miles to the gallon and 62 miles to the gallon. It's also notable that when we're at small numbers, small increases matter a lot. So when you're looking at trucks that might get 12 miles regularly or 18 if they're a hybrid truck, that's actually a huge improvement. So that's, anyways, this g of x is one example of a rational function. Another one, we won't flesh out as much. It's the Cobb-Douglas utility function. And it's a function from economics. So in economics, economists are usually interested in something that they call utility, which is shorthand for how much do you value something? Not how much do you put a price on, but how much do you value something? So for instance, just as an example of what different values might look like, a really trivial example is just to think about like this red mask I have that I wear. To most people, this mask is probably worth 10 or 15 cents. But, I've been using all of quarantine. I like it. So, I'd probably pay like $8 or something for it. Just because I like it. So it has a higher utility for me. So when we're looking at utility functions, we're like assigning numbers to how much we value something. So one person's utility function might put just the number 2, not $2, just like a 2 on there. And my utility for it might be more like 30 because it brings me joy and happiness, even though it doesn't bring me any more monetary worth. So one common example of a utility function is this Cobb-Douglas utility function for comparing multiple goods. Specifically, we can look at it as comparing 2 goods. My econ professor always used the example of pizza and beer, so that's what we'll do. And so we have this function. It's actually in two variables, but might as well get used to that now, where you can plug in two different inputs for your function, an amount you want for pizza and an amount you want for beer, and then it outputs the utility for you, which is p to the 1/2, b to the 1/2, and maybe you change these 1/2s around, but this says that the goods are about even for you, and the best thing to do is have them. If you study this function, you can learn that the best way to distribute it is to have both pizza and beer in about equal quantities. So for instance, if I have 3 slices of pizza, I want 2 beers, going to hang around at the pizza joint for a while. And then what economists then study is usually looking at marginal utility. Because often we're not thinking about things in terms of how much total, but marginal utility asks how much if we have one more. So how much does my marginal utility go up if I have an extra slice of pizza? And you might imagine that for when I haven't had too many slices of pizza, if I've had only maybe two slices, then I'd be pretty happy to get a third or a fourth slice. But once I've had 7 or 8 slices, someone's shoving pizza down my throat, my utility is going to be pretty low. And so the marginal utility can be found by starting with this utility function, doing something called a derivative, if that means anything to you. If it doesn't, we're not going to worry about it. And so we denote it UP of PB equals beer to the 1/2 2p to the 1/2. So let's say that the place I'm getting pizza at has a 2 beer maximum because they're making sure no one really goes over, and I've been known to drink beers that are like 8% because they're like stouts. So this might be fixed at the square root of 2 if we can only have 2 beers over 2 times p to the 1/2. So we have this function, our utility of p, our marginal utility of how much pizza we have is equal to the square root of 2 over 2p to the 1/2. So what it's saying is that if we plug in 1, my utility, so how much value I get out of having how much value would I get out of having one more piece of pizza if I've only had one, gives us 1 over root 2. That number doesn't really mean anything, but we're going to compare it to the size of if I've already had, what's a nice number to take a square root of? If I've had 9 pieces already, then we get the square root of 2 over 2 times 3, which is the square root of 2 over 6, which equals 1 over 3 root 2. So it's saying that my utility is going to be a third as much at that 9th slice as it was at that first slice. And so that's because we get that our function is now kind of like decreasing because we're dividing. So as we plug in larger and larger values of p, we're getting smaller and smaller and smaller. And maybe if you're thinking more about it, this is only good for small values of pizza, because at that million slice of pizza, it's still saying I'm getting positive utility out of having one more slice. But let's be real, at a million slices of pizza, I'm probably dead. At which point I couldn't have any more utility. Anyways, so this is just an intro to two examples of rational functions. We won't be really focusing on economics at all, but I thought this was just an interesting example. Rational functions, for what we're going to see right now, don't pop up too often in ways that we can understand at the college algebra level. Because the functions they model are usually pretty weird, such as like this marginal utility, where we're looking at not a utility function, but how our utility function changes as we add one more. So this is what we can see in other applications, like in biology, we might be looking at populations, and then as population changes, like as population is going up, we might have that a value is going down. So these come up in pretty tricky applications. If you know any applications of rational functions, I would really, really like to hear about them because I honestly don't have too many, at least not that are explainable at the college algebra level. All right, signing off. I'll see you in a couple of videos. Well, I'll be producing a couple more videos so that way we can actually understand how rational functions work, what their domain is, and how to graph them. All right, see ya.